I know. I'll lean in a little bit more then. All right. So I'm going to be talking about ring minus 1, ring minus 2, or essentially, like, you can't hear me? All right. I'm going to be talking about ring minus 1 versus ring minus 2. Ring minus 2 is a colloquial term. We'll get into that in a sec. Pete Markowsky, some of you may know me, some of you don't. I'm a senior security researcher at Crucial, which was bought up by the Harris Corporation last April. Before that, I used to work on like SBIR research related to like hypervisors and other stuff. So what are we going to talk about? System management mode interrupts, system management mode interrupts, virtualization on the AMD platform, and the interplay between the two. Like essentially, when you can get execution, which one runs, when it does, and which one can supersede the other. Why should we really care? Well, like I told you a few seconds ago, when I was working on SBIR research, we were trying to build a hypervisor that was essentially designed to isolate a process from a malicious system. The goal was even if the attacker had root, that they shouldn't be able to get at the executable on disk because it'll be encrypted. A symmetric key would be stored inside the hypervisor. You would use that hypervisor and like page table trickery, thus to hide the executing copy of the code from the rest of the system, so that only the hypervisor and only the stuff with the key would be able to get to it. The thing about this is normally system management mode, like that code runs outside of the protections of VMMs on AMDV. If you look in the manual, like it's highlighted where it says, oh, by the way, you can just you let system mode interrupts be taken normally, and this will run outside of your VMM. So for someone like myself who's afraid of possibly having like code that could be injected into a system management mode, and then you could use that code to read things like keys, that becomes a big problem. So our assumptions are that the attacker has the ability to install an SMI handler. They could take advantage of like BIOS overwrites or cache attacks. Like some people have probably seen like the Week to Floats, and I'm maybe butchering his name, so please like let me know if I am. Basically, the problem is like we assume they can install the handler. They could have like root or system privileges in the guest where they can load drivers and everything else. And they may have even subverted the BIOS up to a point. So where they can actually install the handler by having their own like crafted BIOS. You could take something like Core Boot, which used to be Linux BIOS, roll your own system handler in there, throw it back up, and there you go. And now you have something running in system management mode. So again, to sort of restate the problem graphically, because it's always better, you'll notice that I definitely can't do art. That's why I'm doing this. Essentially, what you have is you have in the upper corner over here on the left, you have a virtual machine monitor. And it's running, and it's executing, and it's putting guests over here. The problem is the system mode interrupt happens. It goes over, like execution gets transferred to the SMRAM, which is where the SMM code lives, rather. And to put it bluntly, this happens, and it has full access to RAM. So this is the problem. So what is it? System management mode is essentially a 16-bit operating mode similar to real mode on x86. It's supposed to be transparent to the OS. What that means is that when it gets invoked, execution stops, state is saved, execution is transferred over to the code that runs in system management mode. It happens, and then it's supposed to resume such that the instruction then can begin running again, or where the operating system was when the system mode, management mode got changed into, can be resumed immediately, as if nothing had happened. It's supposed to be entirely invisible to the OS. The OS doesn't know about it. The OS can't find it, shouldn't see it. Originally, this was designed for power management and other stuff, and introduced with the 386. So it's been around for quite a while. You only get into system management mode when there's a system mode interrupt. And a system mode interrupt is only asserted by hardware. Again, like I said, this is called ring minus 2 because really there's normally no restrictions to the I/O or the memory. It's ring 0 code starting out in 16 bits. And it basically has access to all of system memory. And you can, there's some restrictions, not restrictions, but there's some caveats as to how you go about this. But essentially, for the sake of our talk, we have to assume that if you have code in system management mode, then you can basically touch all of system memory, not just what the BIOS gave the OS. So like I told you earlier, system management mode lives in a place called SMRAM. It's a range of physical memory. it's defined, like you can find the start of it because there's a model-specific register called SM base. This points to the start of it. On AMD 64, the default size is 64K. Though using other registers, you can actually set that between 32K and 4 gigs. So where does this all come from? Like, your SMRAM gets configured and set up by the BIOS, or the system firmware. What happens is BIOS will set up SMRAM, essentially copying a handler into it, configure system management mode, model-specific registers, and then it'll simply lock access to those registers by setting a bit in the hardware control register called the SM lock bit. The idea is that by controlling these registers and then configuring them appropriately, you can prevent getting access to SMRAM. And the way this works is that there are two segments that are provided in which, there are two segments of physical memory that are provided such that reads or access to them is denied unless you're actually in system management mode. On AMD 64, you have the A seg, which is a legacy segment, and they have the T seg, which is defined by two model-specific registers. The reason for this is that way you can reposition the code later, so that if you have a BIOS that needs to use like legacy, have more compatibility with legacy operations and use like lower ranges of memory, you can actually move it to a higher range. And the SM mask MSR actually has like 2 bits in it for the A seg and the T seg that say protect this, don't protect this. When you enable those bits, you essentially can't get access to those segments unless you're in system management mode. So what is a system mode interrupt? Essentially, it's a non-maskable interrupt that takes priority over all other interrupts. There are 2 types: internal, which are generated by hardware in response to like in-out and ins-out instructions or IO-IO instructions. Which ones depend on like the logic you have in the motherboard. External ones are like generated by hardware. So you could have something that goes off like a thermal alarm or whatever. It says I need to spin up a fan. It switches modes over. And this causes you to switch into system management mode. Essentially, what this diagram says right here is, this is like all the operating modes you have in AMD 64 and AMD. Essentially, the gist of this diagram, as complicated and as weird as it is that pretty much at any time you can switch into system management mode, provided there's a system mode interrupt. So during a system mode interrupt, what happens is the processor stops fetching instructions, waits for currently executing instructions to finish and buffered memory writes to finish so the state is clean and everything's solid. Copies all of the appropriate registers into this SMRAM save state, and then changes the instruction pointer to start execution in the SMI handler, which exists at SM base. So it exists at hex 8000 inside system management mode, or SMRAM rather. So the handler itself is really just it starts out as x86 real mode code. So 16-bit code, and it it just runs normally. It could set up long mode, it could set up protected modes. You can actually get access to more stuff, set up paging, set up software interrupts. And then when it's done, it uses the resume instruction, the RSM, which signals that it's time to leave system management mode and return back to the previous operating mode that was invoked when the SMI was asserted. In a lot of papers, like a lot of stuff like in FRAC and other stuff, they've tried to do, get more access to things and actually show off how this works and how to get access to all of memory from this. What happens is they found that address translation is somewhat difficult. And the reason for this is that you have to actually read the CR3 value from the save state area and then actually sort of walk the page tables by hand and implement your own walker to go find stuff and to go figure everything out. Oftentimes a lot of privilege escalation attacks and other stuff that would come from this, what'll happen is they'll actually overwrite values in the save state area, and then they'll invoke the resume instruction, which will then read the save state and immediately say, oh, my instruction pointer, DeFloat's original attack that he presented at CanSec West back in '06, what he did was he actually modified the save state area so that it would contain the instruction pointer of his code afterwards in ring 0. So the idea would be he would bypass everything by saying, oh, okay, when you get out of this handler, call resume, run this code over here, now it's running as privileged, it modifies data structures and goes. So again, how do we install a malicious handler? There's a few ways you can do this. Simplest in terms of like development time is in a lot of ways is just install a modified BIOS. Get something like core boot, set it up, like hack into it, and just write code to DRAM the same way the BIOS would. Is you're just writing your own handler. It just has to read keys or values from other parts of DRAM. Other things that people have done, they found like the Invisible Things Labs people, they found a bug in the SMI handler for the Q35 stuff, and were able to use that to get their code into SMI, or into SMM rather. And from there, they were able to do all sorts of stuff. And then there's the other attack that came out at CanSec West last year, which is where by manipulating x86 caching, you're actually able to say, well, this copy of SMRAM is cached, and it's mapped as write back, and so you're going to end up doing a whole bunch of writes to the value of SMRAM that even though it's not mapped because you're not in system management mode, the idea is that the L1 cache is going to be populated with your data, and then all you have to do is trigger a system mode interrupt, and then rather than fetching the data from SMRAM, you end up fetching it from the L1 cache, in which case you have this sort of disparity between what's in the cache and what's actually in SMRAM. So, like I told you before, my thing was we were building a VMM. The goal was to isolate a process from a malicious system. So we have to assume that the attacker has the ability to do pretty much whatever they want on the box, provided that our VMM can isolate them. So our goal out of this is to actually say, can we take system management mode and like isolate it and make it subject to the protections of the virtual machine monitor? The nice part is that if you look through the developer docs and everything else, this is actually part of the design. So the goal of this is what's called containerization, or to put all of the SMM code into a virtual machine so that its execution can be constrained. All right. So one of the things that's interesting is that the memory controller got moved into the CPU for AMD 64, which means that all accesses to DRAM go through the processor, go through all the states, so we can control the horizontal and the vertical in that regard with page table trickery and other stuff. So we don't have to worry about like the North Bridge being off to the side and being configured differently. So what is AMDV? AMDV is the x86 64 like virtualization extensions for AMD. It's based around the VM run instruction, and I'll show a diagram on how that really works. But the idea is you have a VM run instruction, you have a VMCB, and together the VMCB defines exit conditions, or when you would transfer control back from your guest back to the virtual machine monitor. At which point you have the state of that virtual machine inside the virtual machine control block from, like, it's saved on the exit. At which point, looking at the diagram here, it's a little bit more clear. You have a virtual machine control block. It defines like what state happens when you call a VM run. Like where do you go in the guest, what happens, like all of your sort of state at the time of the invoke, or at the time it's invoked. When the guest continues to run, right? And when it encounters one of those conditions that you've said, like, say for example, you said, like anytime somebody writes the address 0x90, I want it to exit back to the VMM so I can control it. When it sees that there's a write or read to 0x90, that would cause a VM exit. The VM exit would then go back and immediately resume execution in the VMM right after the VM run instruction. At which point, all the data that was, or the state of the guest was captured inside the VMCB. At which point you can then check the exit code in the VMCB to see why did I exit, what did I do, how do I have to handle it, and you have your handler code right there. And the idea is you would do this, handle it, emulate whatever operation you need to do. Maybe you don't let the write go through. Maybe you like make it go somewhere else, whatever else. And then you sort of continue in this loop infinitely. Like you just sort of like, okay, run the guest again, run the next guest, do whatever you got to do. All right. And this goes on. So a few of the key features that are going to be used, that we're going to use in order to actually put the system management mode into a virtual machine. We need the ability to actually stop SMIs from being asserted, because we can't have this going on while we're trying to like clean it up. It's just a matter of like keeping state atomic, or in sync rather. So they added this thing called the global interrupt flag. Now the global interrupt flag, when it's set to 1, allows all interrupts. But when you clear it, everything is stopped. Everything is held pending. Like system mode interrupts are actually held like on the line but not taken, so you don't actually go to the SMI handler, but the line is still asserted. Paged real mode allows you to actually like virtualize 16-bit like execution. It's a mode in which paging is still applied to 16-bit code, which doesn't normally have that concept. And the last important feature that we're going to use is the system management control register. And what this does is this actually lets us control whether or not we can map SMRAM or whether or not the actual SMI handler is invoked directly, and whether or not, and it lets us also clear the line as well, just by simply writing bit patterns to the appropriate MSR. Like I said earlier, the virtual machine control block has two parts. It has a state save area, which contains guest state, and it also has a control area, which defines which interceptions, what are the conditions we actually want to intercept. The things we care about for isolating SMM are the SMI bit, which actually says when there's an SMI asserted, exit out of the guest and and proceed back to the VMM. The other thing we need is we need the RSM instruction, because the idea is that if we're going to run the system management mode code inside of another virtual machine, that we're actually going to need to control not only when you enter SMM, but also when you exit out of it, because when you exit out of it, as I said earlier with the sort of defloat attack, modifying the state in SMM will affect the processor when you resume. And so we need to be able to control both the entry and the exit. The other thing that we're going to be interested in is interception of IO instructions. Again, this is because we know that there's going to be hardware configurations in which certain instructions will actually cause the hardware to then assert a system mode interrupt. And the last thing that we're going to care about are the model-specific register intercepts, or MSR protect. The reason for this is that once we get access to the SMM MSRs, that means we've disabled it, and if we don't intercept it, then privileged code in the guest could then start messing with it. Or also we have the problem of a malicious SMI handler might actually try to mess with this stuff as well. So how do we deal with SMIs? The AMD64 Programmer's Manual offers 3 solutions. The first one is simply don't do anything. What happens is that when an SMI is asserted, which I had it in the diagram earlier, basically all the register values that are populated in the save state area are from the guest, if it's taken in the context of the guest. Which is sort of their solution. They're well, you don't have to necessarily do anything. It's going to be really hard to get to other values because you've controlled CR3, you've controlled all the save state because you're controlling the guest, and it'll just run. The problem with this is that, again, it assumes you may have a handler that might be trusted, or it's just the simplest solution. But again, the VMM protections aren't applied, so if somehow you're able to get code in there and it's able to access memory, you're kind of boned. The other solution they offer is that you can intercept all the IO instructions that can cause an SMI. The problem with this is that, one, it's going to be complicated. It's going to be incredibly tied to whatever hardware, specific BIOS and platform you have already set up. And potentially, if you already have a replaced handler, it doesn't necessarily stop that. It just sort of stops you from invoking it through an IO instruction. So if the hardware still goes off, if you find a way to maybe stop a fan, or maybe take a blowtorch and put it next to a server box or something until a thermal event is triggered, you still could potentially run your code. And the last solution, which is what we're going to go over, is actually containerizing the SMI handler to run inside of a virtual machine. The way this works is there's really 2 solutions for this. The first solution that they offer in the manual is to create another hypervisor. So when you get access to SMRAM, simply replace the handler itself with another set of code that ends up creating a virtual machine monitor that exists inside SMRAM. The idea being is that when the handler gets invoked from a system mode interrupt, this VMM creates another whole environment inside SMRAM where it's okay, this monitor and this other monitor work together such that the system mode interrupt happens in SMRAM, it sets up a virtual machine control block, and then runs the original handler with that configuration. The idea being is that if you then try to write to other memory or other stuff that isn't in SMRAM, you'll get an exit, the exit will go back to your new VMM, and you'll just exit out and run, everything will be okay. This is a fairly complicated thing to do. It also requires you to bootstrap yourself up from real mode. It's fairly more complicated. It's not the solution I went for when I was actually working on this. The other alternative is to write code in the VMM to actually emulate switching to and from system management mode, and then run the SMRAM code inside the virtual machine. So again, like, the important thing to note, though, about intercepting SMIs is that we have this bit inside the virtual machine control block. And what happens with the intercept is that it says, okay, when this is asserted and the SM lock is 0, when I get an SMI, transfer control to the virtual machine monitor. If the SM lock is set, which a lot of BIOSes will do to make sure you're not messing with this from the OS code, that actual SMI intercept is ignored. The hardware just doesn't actually set the intercept, and the original handler is invoked. So once that bit is set, you're kind of in trouble. So you need a mechanism for unlocking that bit. These are the steps that you sort of have to follow in order to containerize an SMI handler. Like I just said, you have to ensure that the hardware control register, SM lock bit, is 0. You need to get access to SMRAM. Because system mode RAM or SMRAM exists, and system management mode is basically a 16-bit operating mode, it's expecting not to have I'll just go through each step and then explain it step by step. I'm getting ahead of myself. So the first part is you need a mechanism for ensuring that SM lock is 0. If it's 0, all related MSR, all SMM related MSRs may be written to when you're in ring 0. That means you could reconfigure the handler on the fly, which creates some really weird configurations when you experiment around with it. And they actually provided you a mechanism, which is another model-specific register called SM key. And what SM key does is, if the system management mode lock is set, but before you set it, you happen to do a write to SM key, it basically becomes a password that allows privileged code to unlock SM lock. The thing about SM lock is that if SM key is not set, and it's set to 1, the only way to unset SM lock is to actually reset the machine. So again, when I said earlier that you could have a BIOS, if you could have somebody who subverted the BIOS, they can subvert it up to a point. Provided that they actually leave, if you're expecting an SM key value to be set before the SM lock is set, then you can always unlock the bit. If they don't do that, and if they don't actually set SM key for you the same way you expect it, what'll happen is that when you go to check for it, as you can see in the sort of pseudocode I have up here on the right, essentially you know that you have an uncooperative BIOS. You're going to assume that if you're going to build a system like this anyway, your BIOS has to cooperate with you to get around this. So you know you're sort of boned at that point. So it's all right, I mean, in my case, I was just halting the machine if I couldn't find that. I also discovered while developing that I was using the AMD SimNow simulator. I discovered that in some configurations, including the one I did most of my development on, it didn't actually support the SMM key MSR. And if anybody's seen me ranting on Twitter about random outputs where I was offering $100 to anybody who could explain what it was, it turns out that what it was me writing into the MSR and just having the simulator go, I have no idea what to do with this. So, followed by crashing. All right, so now that we've made sure that we can actually turn the bit off, right? So we've turned the SM lock bit off. We need to get access to SMRAM. The problem is SMRAM is supposedly only accessible from SMM. Again, like I mentioned earlier, there's a system management mode control MSR. What this does is it lets, by writing certain patterns into the MSR, we can simulate different portions of system management mode. So we can say, okay, SMI enter. What that does is it actually says, okay, I'm going to map SMRAM, put it up there, and then you can start copying from it directly from your privileged code in the virtual machine monitor, or you could even just set up page tables and everything else in place using SM base as the start of your virtual machine, and you figure out the size of SMRAM, at which point you have access to it. The other thing too is that by doing this, you also prevent other SMIs from being asserted at the same time. So all right, so like I said, you have to run this in a virtual machine. In order to run a virtual machine, you basically have to allocate and configure a virtual machine control block for what I'm calling the system management mode virtual machine, or SMM VM. One of these days we'll come up with better terminology, because I'm just going to stumble over it if I keep saying it all the time. But in order for this to work, the specific requirements are you need to be in paged real mode. Paged real mode is an operating mode in which your virtual machine protections, all of your virtual machine monitor protections for memory are based around the concept of paging. Real mode code and 16-bit mode code assumes that there are no page tables and assumes it just has raw access to memory. It's based on the segmentation model where you have like a segment and an offset, and that's your address, and it figures everything out from there. So in order to apply memory protections to this kind of code, you need page tables. So they added the paged real mode, which actually lets you set the paging to 1 and protected mode to 0, which is actually an illegal processor state unless you're in a guest. You need to be able to set CR3 to the physical address of like of the guest page table, which is really a shadow page table, which since SMM doesn't actually use a page table, it doesn't use paging. This is just your shadow page table to translate addresses. Then you need to set like the virtual machine control block to intercept page faults, because you're going to run into that where you have to update page state and anything else because memory will be accessed. And finally, because you have to control the return from the system mode interrupt handler, you have to intercept the RSM instruction. The other thing that's important to do is also do it like, if you have a malicious handler, it may try simply to disable the system for some reason. Let's say you have like an availability scenario or whatever. There are a bunch of states that are like very illegal to run an SMM, like when you're running an SMM that you can't do. Some of them, unfortunately, are not coming to mind right now. But basically, you need to intercept like shutdown, because if any of these conditions are met, and it causes a shutdown and you're running as a virtualized guest, but you don't actually catch shutdown, then the processor is just going to shut down. You lose the whole machine. Or it turns itself off, really. And the last thing is that since we're opening up SMM lock, we need to make sure that we control, the virtual machine monitor actually controls access to the system management mode MSRs. So we need to intercept all of the writes to those SMM MSRs. And basically, we sort of virtualize them where we just say it doesn't happen. Say, all right, you tried to write to it, intercept it, get rid of it. Okay, and so now we have our guests. And what do we need to do for our guests? We need to prevent writes to MSRs by configuring the model-specific register permission map. We need to make sure that we intercept writes to the hardware control register, because if somebody has the ability to reset SM lock back to 1, all of our intercepts go away. At which point now we're in a lot of trouble because we've lost the ability to virtualize or to containerize this. The other thing too is that since we've set SM lock to 0, we need to make sure that any of our guests don't attempt to move where SMRAM actually is in the system. Like you could just put SMRAM somewhere in DRAM. So we need to make sure that they don't try to just install their own handler somewhere off on the side. So that means controlling SM base, SM adder, SM mask, and anything in terms of SM control or even SM key. Because if they want to, when SM lock is 0, when SMM lock is 0, if you set a write to SM key, you've now reset the password. So potentially, if we had to lock it again, we couldn't unlock it. All right, so again, like I said, page real mode required this, paging. So we had to create a shadow page table. Linear addresses in this case are actually just the segment and offset that's expected, and that's a guest linear address, which goes from we take that segment plus offset, we map it through our table, and that immediately comes out with a physical address. So we have to actually, when we're doing this and we're actually containerizing everything, the first thing we have to do is we intercept an SMI. When we intercept the SMI, we have to map SMRAM. We create entries for SMRAM inside of our page table. And after we've created entries inside of our page table, and we've configured all of the guests appropriately so that we can intercept this and run it and everything else, we then have our VMCB, which then kicks off and runs from there. But the other thing too is after we intercept, we also have to copy, we basically emulate what we emulate what happens during system management mode, such that we actually are copying the entire save state from the guest, putting it into our new VM, which is in SMRAM. And from there, we just run it. We run the SMM VM, and when we run it until it gets the RSM instruction, in which case we then resume. The nice part about when we copy this and emulating this is that we can filter out known values before we return to the guest or when we're coming from the guest. So that means that if suddenly we notice that the instruction pointer changed wildly before this somehow, then we know that potentially the SMI handler could be doing something like trying to invoke code at ring 0 so that it can then like modify OS data structures, or possibly even copy out RAM. Like I said, I was trying to protect potentially a symmetric key living inside the hypervisor. So maybe you copy that, put it into one of the registers, put it into the save state area from your system mode interrupt handler, and then you want to put it back in your guest so that your attacker can actually get access to it and then pull executables off. All right. So I actually tried to do all of this. Apologize for some of the burbling, but let's see if I can get this going right now. All right. So I'm going to reset this. So what I did was I took the malware analysis virtual machine monitor that was written by a bunch of students at Carnegie Mellon University. It was actually originally based on this academic one called Tiny Virtual Machine Monitor. And I took it and I actually modified it such that it'll take the platform system mode interrupt handler and it'll run it inside of a virtual machine. The way it works, and so over here we have our serial output. I'm going to run it again. There we go. Okay. So you can see SimNow is running. It's reinitializing everything. I'm just using the BIOS that came with right now. I had a modified version of core boot. The thing you're going to see with this is I'm going to virtualize the system mode interrupt handler, but I have a little bit of bug. I have one bug in my code involving paging and the shadow page table such that when the virtualized SMM handler runs, I'm getting the general protection fault you can see on entry. So I just need to fix some of that code right there to make that go. So all right, so here we are. So BIOS is booted up. I'm now going to run MAVMM, which is going to virtualize this environment right here. So what's going to happen is I'm actually going to save the state of the system right now at boot with grub, copy that into a virtual machine control block, and when it goes into the virtual machine control block and VM run is run, we're actually going to come back to grub again, except this time we're going to be operating inside of a virtual machine. At the same time, while I'm loading this, I'm also mapping SMRAM, copying all of the contents of SMRAM, putting it on a bunch of other physical pages in DRAM, making a virtual machine out of that by defining a virtual machine control block, and setting the appropriate intercepts that we covered in those slides that I sort of raced through. And when that's done, what's going to happen is that every time the guest gets a system mode interrupt, I intercept it, I go through all the steps I just talked about, and I invoke the original system mode interrupt handler in my virtual machine. And let's do this in a sec. So all right, so here's this console over here. Go. All right. So going through all this, we check all of this, we boot MAVM, it figures out where all physical memory is. Our VMM code ends over here, is mapped at 800,000, or yeah, sorry, 8 million hex. We initialize all of this, we have our VMM memory allocation set up. We figure everything out in terms of the features. We create our guest, like I told you, where we save the state of grub at boot. Load everything else. We build our page tables for both the guest here and for the SMM VM. All right, and like I said, so we get all of this, we boot through, we go to grub for the second time. This is my output right here, just to make sure that I'm actually getting through the sort of loop. And then I end up switching to page real mode because I actually caught an SMI. At which point, I then run the virtual machine, but as you can see right here, the SMM handler is causing a VM exit, and this is the general protection fault that I told you about that I need to fix in order to get the demo complete and able to handle non-trivial system mode interrupt handlers. Because I'm pulling this right now out of the BIOS, or out of the SMRAM. So right here, you can see that I got the protection fault. I need to figure this out. But I resume it again, at which point I move it forward a little. I move the instruction pointer forward a little bit, and I actually get the RSM instruction, which I then trap back from the SMM VM. And currently, right now, I'm running what I call my test OS. It's just an instruction that jumps onto itself. So there's nothing real. I just need a guest to just constantly run in guest mode. And that is my demo. And that's sort of my talk. So actually, figured. So basically what happened, like I said, was we caught the SMI here in guess A, which is what we had after grub. We immediately come back to right after where we ran the VM run instruction. I check the exit code, and I go, oh, I got an SMI. And from there, I do what's called SMM VM prep, which is map SMRAM, set up the page tables, get everything going. Call VM run on that again, which then puts us in our guest SMM. In this case, I got another exit, which is for the general protection, keep it going, and I exit out again when I get the RSM after. So if you're trying to build a secure system and you actually have to do all of this, you do need some cooperation from the BIOS, which is, like I said, to make sure that you can actually unlock SM lock, otherwise you can't really do any of this. And so as part of this, you sort of have to bootstrap a virtual machine monitor. You can use like SK-init to actually do this after the fact, provided that the BIOS has agreed to let you unlock SM lock using the SM key, MSR. So what happens with SK-init is it's going to stop all their processors other than the bootstrap processor, which is the one that invoked the SK-init instruction. Reinitializes processor state as if a reset had been asserted, and then you can use like minus some of the SM lock stuff. Though I need to check on that again. And then you can use like device exclusion vectors to keep like DMA and other stuff away from you from being hurt, like attacked. But the most important thing about this whole thing is that when you're loading it, the global interrupt flag is set to 0 while you're running SK-init code until you, as software, unset it. And that way, your secure loader, which then loads your virtual machine monitor, it can actually do all of this atomically, and so you don't have to worry about like system mode interrupts getting taken or handled while you're trying to do all of this. As well as you get the added advantage of having the ability to verify the integrity of the secure loader, like by using the TPM. So I quickly looked at a lot of the stuff that would be, like, I looked at Intel's VT to figure out how they were doing this as well. The technologies are conceptually very similar. Important things that are sort of different are like the VMCS, the virtual machine control structure that Intel has. It's a variable length data structure. And not all features seem to be supported across everything that supports VT. Again, the other thing I couldn't find was I couldn't find an explicit intercept for system mode interrupts defined in the data structure. I need to look again just to make sure that's correct. But when I looked through the manual, what they had was they had normal treatment and they had dual monitor treatment. Dual monitor treatment is essentially what we talked about earlier, which is you can put another hypervisor inside SMRAM. They have another model-specific register that you can use to map SMRAM, sort of the same way that SMM CTL does. Lets you. The thing is, not all VT hardware supports it, so it's like the second or third sentence in the section. And I have to look at more at how that works and more of like the interplay between that. The other thing too that's kind of important is that Intel's VT uses virtual 8086 mode to virtualize real mode code. And sometimes you need other code to sort of virtualize real mode code. This is where you get things like VMX assist from Zen in order to boot operating systems and whatnot. Anyway, thanks for coming. Thanks for coming to Shmoocon. Any questions? All right. The question was, is this stuff actually being used in any Harris products, or was this me trying to figure out how to containerize SMM? The answer to this is that the research I was originally doing was to build that other VMM, and that was an SBIR that we had back when we were Crucial Security. This is sort of an offshoot of that work because I saw the Invisible Things Labs talk last year at Black Hat DC and sort of realized, like, oh crap, this may be a way to get at our keys and start decrypting stuff. So all of this right now is completely sort of academic stuff that I've been doing with Harris, but sort of on the side as well. Mostly so we have the research so that when we do get back to developing that product, we can actually like take care of this threat.
Do you think there's any commercial hypervisors which are actually trying to do this now?
Commercial, I haven't really looked at a lot of the commercial stuff. Everything I've looked at has been the open source stuff because it's available. So I can't speak to like Hyper-V or any of that stuff. The platform does support it and is one of the design features. I'd have to look at it to figure it out. Anyone else?
Have you read the, or I guess what would be your thoughts on the implications of this for the SMM rootkit paper that came out in Frac? Does this effectively manage that end up being caught within the virtualization?
If I remember correctly, the question is that does this effectively deal with like the SMM rootkits that came out in Frac and like the last issue or the one before that? If I remember correctly, they're trying to actually take advantage of chipset stuff where they use the IO instructions in order to actually set up values inside the chipset. Because you can intercept those instructions by defining conditions inside the virtual machine control block, you could essentially mitigate some of that, but you have to, again, build logic around it. I'd have to look at those papers again, but I think my initial reaction is yes, I think this would take care of it. All right. There we go. All right. Anyone else?
How could this be used for evil?
How could this be used for evil? I don't really have a good use for that. What would it take to boot MS-DOS? Inside of a virtual machine or inside? In SMM? I would have to look at it, but basically you'd have, it is 16-bit mode code. Yeah, you can do software interrupts from SMM. All right. Okay. The performance, because this is all happening in hardware for the most part. All right. Yeah, sorry. The question is, what is the performance impact of all the context switching back and forth? The performance impact for a lot of the sort of hardware accelerated stuff, like in the guest, not so much. When we switch out and we end up doing system management mode inside of the virtual machine, because it's a shadow page table and we have to emulate the paging and everything else in software in order to control it, there is a distinct increase in overhead. I haven't benchmarked it to really see how much of an overhead increase it is, but given that shadow paging and software paging is one of the biggest performance bottlenecks for virtual machines, it's certainly not zero. It's probably somewhat significant.
You say something about the segmentation in SMM mode. You said that effectively it has access to the full 4 gigs of RAM, but it's 16-bit mode. So how does the segmentation actually run? You said it expanded the segment descriptor or something like that?
Yeah, the segment descriptors are extended all the way to 4 gigs as part of SMM. So the question was, it's 16-bit mode, and how does it actually get access to all of system RAM? Now, by default, it won't actually be able to address more than a meg, just because it's in 16-bit mode. However, you have the 32-bit override, or you have the override prefixes in x86 that'll let you do 32-bit instructions inside of SMM. So you can actually get access to more. The other thing you can do too is you're starting out in real mode, or real mode-like operating mode, and you can in fact bootstrap yourself into long mode or protected mode from there. Anyone else? Oh, over there.
Does this offer any protection if you have a malicious virus
Like I said, up to a point. The point is that provided that the virtual machine monitor is able to get control of SM lock, meaning that SM lock is able to be set to 0, where you use like SM key to set that, then you can use the virtual machine monitor and SK init after the fact to bootstrap your way through. But if the attacker, in fact, just says, no, SM lock is set, there is no password, then you really can't do anything to stop like system management mode at that point, because you lose all the interceptions.
Where can we find my motherboards protected using this kind of method?
Okay, the question was, where can we find motherboards that would be protected using this method? It's not really a question of the motherboard as much as it's a question of the BIOS. So which BIOSes are actually set up with keys and whatnot to do this. Off the top of my head, I don't know. I was using core boot for most of my experimentation, so I was controlling the BIOS just to see how the features actually worked. But it would be something like worth looking into. All right. If anybody's actually interested in seeing the code and other stuff afterwards, I'll be in the bar. I can't distribute it because there's some licensing stuff with CMU, the way they put up MAVMM. So as soon as I work that out, hopefully I'll be able to clean up the code and patch it and release it. But if people are interested, I'll be downstairs in Harry's Pub, and I can show you what I did. All right, thanks.